And it depends on what type of plate we have as far as what type of activity takes place here. And most of this is below sea level. So below sea level, and if we look at this map, again, we'll note the trench zones are at the edge of many of these plates. Here's the North American plate here, coming in contact with the Eurasia. The South Atlantic, South American plate, coming in contact with this plate. So these things either pull apart at plate boundaries, come together at plate boundaries, or they slide past one another at plate boundaries. So you have literally convergent activity where they come together, divergent activity where they move apart, or transform or transverse, depending on your book, if they're sliding past one another. An example of where they are sliding past one another is the San Andreas Fault in California. In the San Andreas Fault of California, we have two big blocks of lithosphere literally sliding in different directions. Okay, because of this activity, at the plate boundaries, we'll find that most earthquakes on planet Earth are associated with the plate boundaries. Notice the earthquakes here in South America, earthquakes in North America, earthquakes in Alaska. And you can compare those to, again, the trench zones, the convergent plate zones up in the Aleutian Islands off the coast of Washington and Oregon. So earthquakes definitely related to where the plates are moving either toward one another, away from one another, or literally parallel to one another. Okay, so we have plates that make up, again, 7 major plates that make up the bulk of planet Earth. Now, Wegener looked at various ideas before he proposed this theory. And Wegener was a scientist, first and foremost. And as a scientist, he gathered a lot of information before he proposed the theory. He just did it one Saturday afternoon, so I want to write something for the masses. And I think many of you at one time or another have looked at a world map and you saw that South America and Africa might blend together. And Wegener and others saw this. People saw this as soon as maps became available, that some of these things can fit relatively closely. Well, one of the things Wegener did was he tried to realign the continents. But unfortunately for Wegener, he could only do it at the shoreline, because that's where the maps were constructed. And he had big gaps and big overlaps. And people said that's unacceptable. You can't have those kinds of gaps and overlaps. After World War II, the Navy had mapped out the oceans. And they mapped out the edges of the continental slope. Remember the continental slope was that part that just dropped precipitously? And they constructed maps using the edge of the continent, not at the shoreline, but along the continental slope. And then they began to move the pieces together. And they found that there was less than a 1% gap or overlap if they tried to put them together on the continental slope. Now, 1% gap or overlap is probably very comparable to a jigsaw puzzle, which are all little gaps involved. So that's kind of a neat idea. It fits together nicely. Does it prove anything? Not yet. It's the first step in a long series of steps to prove that these pieces were together. Being a scientist, again, Wegener went to a process called correlation. Okay, correlation is used to compare sedimentary formations. This is basically how it's done. Geologic samples are taken across the Earth's surface, and this is tens of miles across here. Again, tens of miles. So these are right next to one another. And we look at the rock formations. And they look at the rock formations and how they line up. And they take the age and say, okay, these formations are the same. And everything in between should be the same type of material. These are the same. You're correlating various things. But now you come to a point where this unit isn't carried over. Well, what happened to it? It looks like it's disappeared. Erosion may have taken place. But then you have this stipple pattern that starts up. And again, this may be missing here because of erosion. So they're comparing types of rock units separated by miles. Now, sedimentary rocks are deposited in stationary bodies of water, like the ocean. So Wegener decided, let's do a little correlation study. Here's a rock sample taken out of Africa, a column. This is called a geologic column. A geologic column taken out of Antarctica, South Africa, India, and Australia. Areas that are separated by thousands of miles of water. There's no rhyme or reason these rock units should be the same. They should all be different because they're separated by, again, thousands of miles of water. But if you look at this, you find this red formation is found throughout all of these. You find comparable formations scattered throughout. They're not all precisely the same because of erosional factors. But there's enough correlation that it would lead one to believe that these were all together at one time. Not enough proof yet, but again, additional support. The correlating sedimentary strata, again, was a proof that Wegener used. The skeptics are saying, yeah, but he's all right. He doesn't know what he's doing. Well, something that we all know about here in central Wisconsin, that's glaciation, continental glaciation. We know that continental glaciers must form over land. When continental glaciers come in contact with water, such as the ocean, they begin to melt and begin to disappear. So they must form over land. They move off that land surface, but as soon as they do, they begin to break apart. And when a glacier breaks apart, what is that process called? What? No? What is it called when glaciers, big chunks of glaciers break apart? Man, it's been in the news the last year. Because you have big chunks breaking up Antarctica, big chunks breaking up the Greenland. The process is called calving. Calving. So, when it hits the water, the ice is going to calve, it's going to break apart, separate from the main mass. By looking at glacial evidence, we can identify the direction the ice is moving. So you see these little arrows here indicating direction that the ice moved. So apparently the source area had to be in this region. And it moved out and fanned out, just like the glacier that covered Wisconsin. Started not in the North Pole, but the Hudson Bay area. The Hudson Bay was high and dry when the ice formed. And it moved out in all directions. Same thing happened here. Ice is moving on that direction, this direction, in all directions here. Well, the continents have moved apart, and now we look at where those glacial features are located. Oops. see those glacial features still in Antarctica.